So what we want to do now is discuss the Lebesgue integral of more general bounded measurable functions over sets with finite measure. These sets need not be bounded, they just need to have finite measure. So before I do that, I want to review a little bit of what we did previously. Okay. So remember previously we we computed the Riemann integral of a step function as just the, as you would expect, the area under the rectangles that form the step function. So pictorially, it would just, if the step function, takes on 3 values on these open intervals, then the Riemann integral is just the, the 3 red areas of these rectangles. Inspired by this obvious kind of computation, we define the Lebesgue integral. So if we have, we define the Lebesgue integral for a simple function, rather. So if we have a simple function, so it is measurable and it takes on finitely many values. If these are the distinct values, and if EJ is the inverse image of AJ, the singleton AJ rather, then we can write phi as the canonical decomposition. So particularly these are disjoint, these EJs. E is EJ. All right. And phi is going to be the sum here. And we define the Lebesgue integral to be basically the same thing as the Riemann integral of a step function. Okay. And so using this definition, we proved what you would expect, that if I write phi as the sum here, not quite the canonical decomposition, in particular, the lambda i's do not need to be distinct, whereas the AJs are distinct here. So if I write phi in this way, where these are at least pairwise disjoint, and they're a subset of E, then the integral of phi is what I would expect it to be. Okay? Why do I say, you would expect it to be this? Well, you expect the integral to be linear. So you expect the integral of a sum to be the sum of its integrals, and you expect to be able to pull out constants. So if that's true, I integrate the sum. That's the same thing as summing up the integrals. I pull out the lambda i's. I'm left with computing the integral of AI. Well, sorry, the integral of the characteristic function of AI. Well, characteristic functions themselves are already in their canonical decomposition form. So we know the integral, by definition, of a characteristic function of AI is just a measure of AI. So linearity gives us that we expect this to be true. Okay. And in fact, we used this under this assumption that these are pairwise disjoint to prove linearity, particularly here, that the integral of a sum is a sum of their integrals. Okay. We only proved it for 2 functions, but trivial induction gives us this fact for any finite linear combination of simple functions. Okay. So let's actually use this to go back and prove that this proposition is true without this assumption here. Okay. So we did need this assumption to prove this, because we proved this without linearity, because we didn't know that linearity is true. We used this proposition to prove linearity over here. Okay. But now that we have linearity, let's go ahead and check that we can remove this superfluous assumption that these are pairwise disjoint. Particularly if f is written as the sum here. For the EI is not necessarily disjoint. EI is still a subset of E and has finite measure. Then this integral is what you would expect and what you get from linearity. And the proof is just use linearity of Lebesgue integral for simple functions. Particularly, this is writing f as a simple function. Characteristic functions are simple functions. They take on two values, 0 and 1. Right, so to integrate f, we just, we integrate the sum as a sum of integrals, and we pull out the CIs. We're left with integrating this characteristic function. Well, again, that's just the measure of EI, because this is already in its canonical decomposition. So, check by definition that this integral here is the measure of EI. All right? So, yeah, not super important, but if you're wondering if we can get rid of that superfluous, if we can get rid of this assumption here, the answer is yes. All right, let's get to more important things, and that is how to define the Lebesgue integral of a bounded function over a set of finite measures. So let's say we have a bounded function, set of finite measure. So analogous to the upper and lower reformulation that we had before of the upper and lower Riemann, modified Riemann integrals, we're going to define the upper and lower Lebesgue integrals to be basically the same thing. The difference is E is not necessarily a closed interval, and the main thing is we're replacing step functions by more generally simple functions. Otherwise, these are basically the same as how we reformulated the modified upper and lower Riemann integrals. And just like how we reformulated Riemann integrability, we're going to say f is Lebesgue measurable if these two are equal. So I should mention, as long as f is bounded, doesn't even need to be Lebesgue measurable, these two are always going to be defined, particularly this set here of real numbers is going to be bounded below, and this set's going to be bounded above. And the lower Lebesgue integral is less than or equal to the upper Lebesgue integral. It's very easy to prove, and I'll leave it for homework. All right. And it's a little messy here, but this is psi here. It kind of looks like phi, but this is psi here. Okay. So what this is saying is that to prove Lebesgue integrability, we need to prove that the lower Lebesgue integral is bigger or equal to the upper Lebesgue integral. Okay. So let's prove a proposition that Riemann integrable functions are Lebesgue integrable, and the two integrals coincide. Right. So how do we prove that? Well, let me remind you of our reformulation of Riemann integrability. So f is Riemann integrable, so these two are equal. The sup of all these integrals over step functions that are less than or equal to f on a to b, and the infima of all these integrals over step functions that are bigger or equal to f on a to b. Right? And this common number is the Riemann integral. Okay. So two easy observations. One is that step functions are simple functions. That's trivial. It's very easy to check that step functions are measurable, and clearly step functions take on finitely many values. And also, if I have a step function on a to b, well, since it's a simple function, we can take the Lebesgue integral in the sense of, the Lebesgue integral defined in the previous video and PDF, right here. So I claim that Lebesgue integral is going to be the same as the Riemann integral that we computed well, also in previous videos. It's right here. And this is very easy. The easiest way to do this is write phi and its canonical decomposition and just check that when you use the definition of the Lebesgue integral, you get exactly this here. All right. All right, let's put that to good use. So what that means is that these two sets of real numbers are equal because these two integrals are equal for step functions. All right, well, every step function is a simple function. So this is a larger set than this. Likewise, these two sets of real numbers are equal because these two integrals are equal for step functions. And this set here is larger than this set because every step function is a simple function. And before I continue, I just want to point out a little typo here. We're proving that f is Riemann integrable on a to b, then it's Lebesgue integrable on a to b. So it's a typo. There should not be an e. Instead, it should be a to b. Minor issue. Okay, right. So I just mentioned again that this set of real numbers, is a subset of this set of real numbers, and the same thing here. This set of real numbers is a subset of this set of real numbers. I explained a moment ago why that's true. So let's put these facts to use, to good use to basically finish the proof. Okay, so what does this tell me? Well, it tells me that the lower Lebesgue integral, which is the supremum here, well, forget about supremums for a second. This integral, this set of integrals here, this set of real numbers I mentioned is bigger than this set of real numbers here. Okay, that's exactly the content of this here. Okay. This set here is bigger than this set. So the supremum is bigger or equal. The supremum of this set is bigger or equal to the supremum of this set. This supremum is equal to this infimum. That's from Riemann integrability. Again, forget about infimums for a second. This set here is a subset of this set here. Okay, that's exactly the content of what we have here. Okay. This set is a subset of this set. So then it's exactly this set is a subset of this set. This set right here is exactly what this is. This set here is exactly what this is. Okay. So the infimum of the smaller set is bigger or equal to the infimum of the larger set. And this is the upper Lebesgue integral. Okay. So that proves Lebesgue integrability. Because as I mentioned, this is always true for any bounded function on E. Again, bounded function on A to B. E should be A to B here. Okay. So they're equal. And let's think about what we've actually proved here. So we've proved that, well, this is the Lebesgue integral, this is the Lebesgue integral. these two numbers that are equal are the Riemann integral. So the Lebesgue integral is bigger or equal to the Riemann integral is bigger or equal to the Lebesgue integral, which is what I exactly have here. Well, that sandwiches the Riemann integral between the Lebesgue integral. So in that case, the Riemann integral has to be equal to the Lebesgue integral. So that proves it. Okay. All right. So I should make clear that we still want the Riemann integral. We still like the Riemann integral, and we still use the Riemann integral because particularly we have the fundamental theorem of calculus that allows us to practically compute a lot of integrals. It's just for a lot of theoretical applications, or even not theoretical applications, for applications to probability theory, to mathematical finance, et cetera, the PDE, differential equations. We still want to be able to integrate a lot more functions, and we want an integration process that has better properties than the Riemann integral. But still, this is an important fact because it says that when we have a nice this is an important fact because when we have a nice function, we don't have to distinguish between the Lebesgue integral and the Riemann integral. In particular, we can compute this common number using the fundamental theorem of calculus. All right. So there's one issue here that you might be thinking about, and that is assuming simple functions are Lebesgue integrable, and we'll prove that they are. We have basically two ways to compute a Lebesgue integral. One is by this definition in terms of equality of the lower and upper Lebesgue integral. And the other one is essentially from this note here, which really is using the previous definition of the Lebesgue integral of a simple function. Okay, so this note is just saying that if we define the Lebesgue integral in this way for a simple function using the canonical decomposition of my simple function, then that's going to coincide with this sum here if I write f in a different way as a linear combination of characteristic functions. Okay? So the two better be equal, otherwise we have an inconsistent definition, or rather an inconsistent way to take the Lebesgue integral of a simple function. But worry not, all is well. And in particular, simple functions are Lebesgue integrable, and the Lebesgue integral defined in terms of the upper and lower Lebesgue integrals is exactly this sum here that comes from, again, our previous definition of the Lebesgue integral of a simple function. Okay. So, right. So, and here I'm just reminding you that if this is true, then this common number here is the Lebesgue integral. All right, so how do we prove this? And we're also, I should say, we're justified in writing this because it's unambiguous if we're doing this upper-lower definition or we're essentially using this definition. They're going to be equal. And I just want to remind you that, this is by definition, and basically doing work, we proved that according to this definition, the Lebesgue integral is given by this sum here. All right, so how do we prove this is true? jumping ahead here. So let's say phi is simple on E, and it's less than or equal to F. Okay. Well, so we know how to integrate simple functions. Okay. And we're integrating a simple function according to here the previous definition of simple function, of the Lebesgue integral of a simple function. And we know that the Lebesgue integral of simple functions according to the previous definition is monotone. So then this old definition of the Lebesgue integral is less than or equal to the old definition of the Lebesgue integral, which we proved is the sum here. That's the first note of this PDF. Okay, so what does this say? Well, it says that I is an upper bound. If I is the sum here, then I is an upper bound for this set of Lebesgue integrals. Again, here this is the old definition of the Lebesgue integral. So it's an upper bound for this set here, which is a set of all these integrals over simple functions that are less than or equal to f e. Well, the lower Lebesgue integral is the supremum of all these integrals. I is an upper bound, so, well, the supremum is the least upper bound, so the lower Lebesgue integral is less than or equal to I. Okay. So I want to prove actually that these are equal. Okay. Well, so f is itself a simple function on E that is less than or equal to f, because f is a simple function and f is less than or equal to f. Okay, so I, which is again this old definition of this, the old definition of the Lebesgue integral of the simple function. So f is an A, so the supremum is an upper bound for all these integrals, but this integral here is one of these integrals. So the supremum is bigger or equal to this integral, and the supremum is the lower Lebesgue integral, so they coincide. And homework is proving that the upper Lebesgue integral actually also coincides with I, so that the upper and the lower Lebesgue integral are equal, and they're going to coincide with I, which coincides with the old definition of the Lebesgue integral of a step function here. Okay, so I want to end with a very important result. Actually, before I do that, I want to just go through an example. And again, I'm just reminding you here that the point of this proposition is that this is unambiguously defined for a simple function. Okay. So let's just do an example here. So let's take the Dirichlet function, which we mentioned at the beginning of the course is not Riemann integrable on 0 to 1. Okay, so this Dirichlet function is 1 if x is rational in 0 to 1, and 0 if x is irrational in 0 to 1. So you should check trivially that we can write this as this characteristic function here. So we can unambiguously take the Lebesgue integral of this characteristic function. It's just the measure of rationals in 0 to 1. You know that's 0. So this is despite the fact that, again, this is not Riemann integrable. You can check that the lower Riemann integral is the lower modified Riemann integral 0. and the upper integrals are 1. Okay, very easy to check. Okay, so I want to end with a very important result that says basically any practical bounded measurable function every bounded measurable function, so every practical bounded function over a set of finite measures is going to be Lebesgue integrable. So this Lebesgue integral is defined for a lot of functions, particularly way more functions than the Riemann integral. So in particular, if f is the pointwise limit of measurable functions over a set of finite measure, and if f is bounded, then we know f is Lebesgue measurable, and henceforth it's going to be Lebesgue integrable. So particularly if we have the pointwise limit of uniformly bounded functions, then that's going to be also bounded. It's going to be measurable. So the pointwise limit of uniformly bounded measurable functions is going to be Lebesgue integrable. Okay. So in particular, if we have a sequence of Lebesgue integrable functions, by definition, it's Lebesgue measurable, and it's uniformly bounded. Take the pointwise limit of that function is going to be bounded, which is in stark contrast to the Riemann integral, which we gave a counterexample to that using the Dirichlet function way back in the beginning of the semester. So pretty important result. And the proof is very easy. We've done all the work already. So let's use the simple approximation lemma. Particularly pick simple functions on E where the following is true. This is because f is measurable. All right. Right. So as I mentioned, always the upper Lebesgue integral is bigger or equal to the lower Lebesgue integral. Right. So this is just the infimum minus the supremum here. All right. Well, certainly phi n, sorry, let's do psi n first. Certainly psi n here is bigger or equal to f on E. Certainly phi n here, rather, is less than or equal to f on E. Okay. So this integral is in this set. This integral is in this set. So the infimum is less than or equal to this integral. The supremum is bigger or equal to this integral, but it's minus, so it's less than or equal to. Okay, so we know that the Lebesgue integral is linear on it's linear over simple functions, and we know that this is less than or equal to 1 over n, and that the Lebesgue integral for simple functions is monotone. If you want, you can think of this as just 1 over n times the characteristic function of E, which is a simple function. So this is our assumption, psi n minus phi n is less than or equal to n. Okay. And we integrate this simple function. Again, it's just the characteristic function of E times 1 over n. We get the measure of E over n. This is bounded. This is finite. Rather, E is, sorry, not bounded, but E has finite measure. So you can let n go to infinity to get that these have to be equal. And that proves the Lebesgue integrability of f. Okay, so what I want to do next, in the next video, is prove that the Lebesgue integral is linear in this general setting. And that's actually not the easiest thing to do. But we will do that next time.